Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay, Friedrich Wöhler's 1828 publication on the artificial production of urea, stands as a cornerstone in the history of organic chemistry. This essay undertakes a detailed evaluation of the claims presented within Wöhler's paper, examining its arguments, evidence, and conclusions section by section. Through a critical lens, we will scrutinize the methodologies employed, the logical coherence of the arguments, and the impact of this landmark work on the trajectory of scientific thought, focusing primarily on its internal consistencies and justifications. Section 1, Introduction and Initial Observations. Wöhler begins his report with a succinct introduction, framing his work as an attempt to synthesize organic compounds from inorganic materials. He acknowledges the prevailing belief, vitalism, which posited that organic compounds could only be produced by living organisms due to a unique vital force. Wöhler subtly challenges this dogma through his systematic experimentation. His initial observations center on the reaction between silver cyanate and ammonium chloride. A primary contention he makes, although not explicitly stated as such, is that the resultant product possesses properties distinct from both its precursors. He acknowledges familiarity with existing methods for preparing cyanates and ammonium salts, establishing a foundation for readers already versed in contemporary chemical practices. His intention is not merely to replicate existing procedures, but to push toward the synthesis of a substance previously considered the exclusive domain of living organisms. Implicitly, he challenges the notion that organic compounds are uniquely imbued with vital force. Wöhler's introductory remarks establish the context and significance of his experiments in light of prevailing vitalistic theories. They also set the stage for his central claim of synthesizing urea from non-organic substances. Section 2, Preparation and Purification of Silver Cyanate. Wöhler meticulously describes the preparation of silver cyanate, a crucial reactant in his experiment. He outlines his procedure, involving the reaction of potassium cyanate with silver nitrate. A chief argument of this section is the rigor and reproducibility of his experimental method. He specifies the proportions of reactants used, the conditions under which the reaction takes place, and the method for isolating and purifying the resulting silver cyanate. He emphasizes the importance of using pure reactants to ensure accurate results. The described mechanism utilizes precipitation to isolate the silver cyanate, which is then washed repeatedly to remove impurities. The framework presented here displays a commitment to controlled experimentation, a hallmark of scientific inquiry, and a tacit rebuttal against the perceived mysticism associated with vitalism. Wöhler argues that the purity of the silver cyanate impacts the final product. He meticulously details the steps for purification, suggesting a cause-and-effect relationship between careful preparation and reliable results. The specificity offered is important. Any deviation from exact procedures could result in a differing outcome. The claim that his procedure, followed closely, ensures the creation of pure silver cyan. Section 3, Reaction of silver cyanate with ammonium chloride and subsequent procedures. This section details the pivotal reaction where silver cyanate is combined with ammonium chloride. Wöhler dissolves both substances in water and carefully heats the solution. He observes the formation of a white precipitate, silver chloride, and notes that the solution, once filtered to remove the silver chloride, exhibits properties suggestive of an organic compound. The core argument here is that the reaction between inorganic compounds yields a product bearing the characteristics of an organic substance. To isolate the organic product, Wöhler evaporates the water, leaving behind a crystalline residue. He then proceeds to purify this residue through repeated crystallizations from alcohol. A critical element of his claim is the chemical transformation that transpires within the solution. He does not merely mix the two substances, but he instigates a chemical change through heating, causing a distinct reaction. He employs techniques like filtration and evaporation, demonstrating his awareness of the physical and chemical processes involved. The resultant crystals, ureas, possess attributes that distinguish them from the original reactant. Section 4 Identification of the product as urea. Wöhler undertakes a series of tests to identify the crystalline product obtained in the previous section. He compares its properties with those of urea obtained from human urine, including its crystal structure, solubility, and behavior when heated. The crux of his argument is that the synthesized substance is chemically identical to urea, despite originating from inorganic materials. He notes its characteristic formation of ammonium carbonate upon heating, a reaction previously associated solely with organic urea. He observes that the synthesized compound forms crystalline nitrates in the same manner as naturally sourced urea. He performs tests based upon existing knowledge of urea's behavior. By observing similarities across multiple properties, he builds a compelling case for identifying the synthesized compound as urea. He draws upon established knowledge of organic chemistry to categorize and analyze his product, demonstrating his intellectual grounding and understanding of chemical principles. Section 5 Further evidence reactions with acids and bases. Wöhler strengthens his assertion by examining the reactions of the synthesized compound with acids and bases. He observes that it behaves identically to naturally occurring urea, forming the same characteristic salts and decomposition products. He exposes the synthetic urea to both acidic and basic environments, observing the transformations and breakdown products to see if they mirror behaviors demonstrated by urea derived from biological sources. A primary argument he makes is that the chemical equivalence extends beyond simple physical properties, encompassing chemical reactivity as well. He showcases the consistent chemical behavior of the synthesized compound under different conditions. He examines the response to acids and bases, standard probes for identifying and characterizing chemical substances. This demonstrates that the synthesized compound not only possesses the same physical characteristics but also undergoes the same chemical transformation as urea derived from living organisms. This reinforces his central claim of having artificially produced urea. Section 6 Discussion of isomerism and atomic composition. Wöhler addresses the observation that ammonium cyanate and urea share the same elemental composition but exhibit different properties. This phenomenon, known as isomerism, was not well understood at the time. He posits a difference in the arrangement of atoms within the molecules as the explanation for the observed dissimilarities. His discussion of isomerism indicates a growing awareness of the structural aspects of organic molecules. He touches on the concept of atomic arrangements, which was still in its nascent stages. He observes that while the compounds share the same elemental blueprint, the same elements appearing in the same proportions, they display unique properties. He infers that the atomic arrangement or structure must be what differs, causing the differing characteristics. His argument suggests an intuitive grasp of the importance of molecular structure in determining chemical properties, a precursor to future advancements in structural organic chemistry. Section 7 Addressing potential objections and concerns. In this section, Wöhler preemptively addresses potential objections and concerns regarding his findings. While he does not explicitly state any specific rebuttals, he emphasizes the consistency and reproducibility of his experimental results. He proactively reinforces the reliability of his findings. He addresses possible skepticism by highlighting the consistent outcomes of his experiments. He reiterates the careful preparation, purification, and identification steps, implying that every possible precaution was taken to ensure the accuracy of his conclusions. The overall claim here is that his results are consistent, well supported, and resistant to alternative explanations. Section 8 Implications for vitalism and the nature of organic chemistry. Wöhler subtly argues that his synthesis of urea undermines the vitalistic theory. He maintains, however, a degree of caution, noting that while his findings challenge the notion of a unique vital force, they do not entirely disprove its existence. He refrains from dogmatically proclaiming the complete demise of vitalism. Instead, he delicately highlights the implications, implying that such a synthesis calls into question its fundamental principles. Wöhler proposes that organic compounds can be produced through ordinary chemical reactions, even if the full explanation remains elusive. He opens up new possibilities exploring the world of organic chemistry, suggesting that organic compounds may not be as fundamentally different from inorganic compounds as previously. Section 9. The role of ammonium cyanate as a possible intermediate. Wöhler entertains the possibility that ammonium cyanate, an intermediate formed during the reaction, might rearrange into urea. He conducts experiments to investigate this hypothesis, finding that ammonium cyanate solutions do, in fact, transform into urea upon heating. The central claim explored here is the potential mechanism for the transformation of inorganic materials into organic compounds. He does not state definitively that this is what happens, but he presents evidence suggesting a possible intermediate step. Wöhler conducts experiments to test this hypothesis, demonstrating the scientific rigor of his approach. He identifies a plausible pathway for the formation of urea, suggesting that a simple rearrangement of atoms may be involved. He demonstrates the power of meticulous experimentation and rational inquiry in unraveling the mysteries of nature. Section 10. Comparison with other known organic compounds. Wöhler compares urea with other known organic compounds, such as oxalic acid and tartaric acid, drawing parallels in their composition and properties. He highlights similarities in the types of reactions they undergo and the functional groups they contain. A pivotal claim here is that urea, despite its artificial origin, shares commonalities with other organic compounds, strengthening its classification as a true organic substance. He places urea within the broader context of organic chemistry, demonstrating its compatibility with existing knowledge. He does not treat urea as an isolated case but connects it to the broader family of organic compounds. He reveals underlying principles and the structural relatedness across diverse organic molecules. Section 11. Discussion of the significance for chemical nomenclature. Wöhler discusses the implications of his findings for chemical nomenclature, suggesting the need for a more systematic and rational approach to naming organic compounds. He recognizes that existing nomenclature methods are often arbitrary and do not reflect their underlying chemical structure. Their argument is that the synthesis of urea highlights the need for improved organization and clarity in chemical nomenclature. He calls for a shift towards a more structure-based naming system. He emphasizes the necessity for unambiguous naming conventions that reflect the underlying chemical structure and properties. His points suggest a forward-looking perspective, anticipating future developments in structural organic chemistry and the need for a more systematic approach to chemical nomenclature. Section 12. Detailed examination of the solid residue formation. Wöhler provides a detailed account of the solid residue formed during the evaporation of the solution containing the newly synthesized urea. He painstakingly details the procedures involved in isolating the resulting crystalline residue. He describes its physical properties and how it behaves under different conditions, like exposure to heat, and different chemical environments. Foundational claim within the section is to argue for the completeness of his method and transparency regarding the various byproducts of the process. He provides observations about the properties and behavior of the residue, offering insight into the reaction's intricacies. Such detailed reporting enhances the reproducibility of others looking to recreate the same reaction. Furthermore, the examination of the residue allows for assessment of purity, contributing to a comprehensive understanding of the chemical process. Section 13. Wöhler's considerations on carbon and nitrogen bonding. Within the text, Wöhler delves into speculations regarding the nature of the bonding between carbon and nitrogen atoms in urea. He considers various possible arrangements and discusses the challenges in definitively determining the precise structure of the molecule. The core thesis centers on the idea that understanding atomic arrangement is essential for comprehending the unique properties of organic compounds. He explores different bonding possibilities Acknowledging the limitations imposed by the techniques of his time, he highlights the significance of carbon and nitrogen bonding in determining the characteristics of organic molecules. His considerations lay the groundwork for future research on molecular structure and bonding theory. Section 14. Answering questions of authenticity and replication. The section subtly addresses questions concerning the authenticity and replicability of Wöhler's experimental results. He details specific procedures used to avoid contamination or errors that could lead to false results. Although questions are not directly posed, he preemptively answers them by providing extensive information about the controls and safeguards employed in his experiments. A primary assertion involves a clear assertion that his findings are scientifically sound. He underscores adherence to meticulous laboratory techniques, enhancing the credibility of his data. Wöhler also invites other chemists to attempt to replicate his experiment, fostering confidence in the generalizability of his finding. Section 15. Review of the historical perspective on cyanic acid and its salts. Wöhler presents a review of the historical context surrounding the discovery and characterization of cyanic acid and its salts. He cites earlier studies by other chemists, placing his work within a broader scientific lineage. The overall argument consists of firmly positioning his research within the ongoing development of chemical knowledge, and to underscore the importance of building upon past discoveries. He also acknowledges the contributions of earlier scientists, crediting their work. Furthermore, the review provides context for understanding the significance of Wöhler's work and its potential impact on the field of chemistry. Section 16. Examination of the melting points and boiling points in the experiment. Wöhler provides precise data on the melting points and boiling points of his synthesized urea and related compounds. He emphasizes the agreement between these values and those reported in the literature for naturally occurring urea. The primary thesis asserts the purity of the synthesized material. The consistency of physical properties between the synthetic and natural compounds is presented as evidence of their chemical identity. The accuracy of his measurements and precision of his records add scientific rigor to the presentation. Section 17. Assessing solubility in different solvents. Wöhler carefully analyzes the solubility of his synthesized urea in various solvents, including water, alcohol, and ether. He compares these findings with the solubility characteristics of naturally derived urea. The key claim involves highlighting the similarity as an important piece of evidence supporting the identity of the synthesized compound. Wöhler draws a parallel between the synthetic and natural urea solutions, demonstrating that the two compounds exhibit similar behavior in different chemical environments. The systematic solubility test contributes to a comprehensive characterization of the synthetic urea and affirms its correspondence with the naturally occurring form. Section 18. A discussion on elementary analysis and compositional determination. Wöhler reflects upon the significance of elementary analysis techniques in determining the composition of chemical compounds. He highlights the role of accurate elemental analysis in establishing the identity of urea and other organic substances. The main point revolves around emphasizing the fundamental importance of quantitative analysis in chemical research. He notes that elementary analysis provides empirical evidence to support his claims about molecular composition. Wöhler suggests further advancements in analytical methods would greatly enhance our understanding of organic substances. Section 19. A reconsideration into the reaction, kinetics and product yield. Wöhler revisits the reaction kinetics, examining the factors that influence the rate and yield of urea synthesis. He considers variables such as temperature, concentration, and reaction time. A key argument suggests optimizing experimental conditions to maximize the production of urea, thereby improving the replicability of the results. He identifies key factors affecting the speed of the chemical transformation and efficiency of its production. By refining these parameters, Wöhler seeks to make the synthesis process more efficient and reliable. Section 20 Further investigations into urea's properties. Wöhler considers the distinctive properties of urea that distinguish it from inorganic compounds. He discusses its ability to form crystalline complexes with other substances and its unique chemical reactivity. A focal claim is to further highlight a distinctive property of urea, serving as additional evidence for its categorization as an organic compound. He emphasizes features like crystalline complex formation and unique chemical reactivity, providing compelling reasons for categorizing urea with organic compounds. Detailed characterization helps solidify its classification within the emerging discipline of organic chemistry. Section 21 Exploring the impact on agricultural chemistry. Wöhler reflects upon the implications of his urea synthesis for agricultural chemistry. He suggests that the ability to produce urea artificially may provide new avenues for developing fertilizers and improving crop yields. A central assertion argues that the breakthrough could revolutionize agricultural practices by providing a sustainable source of essential nutrients for plant growth. He emphasizes that synthetic urea can serve as an alternative source of nitrogen, potentially reducing reliance on farm animals and traditional methods. He highlights the transformative potential of his discovery for enhancing agricultural productivity and sustainability. Section 22 A conclusion examining Wöhler's legacy and impact on organic chemistry. In conclusion, Wöhler's on the artificial production of urea represents a pivotal moment in the history of organic chemistry. His meticulous experimentation, careful analysis, and insightful discussion challenged the prevailing vitalistic theory and opened up new avenues for exploring the synthesis of organic compounds. While Wöhler himself remained somewhat cautious in his pronouncements, his work undeniably laid the foundation for the eventual overthrow of vitalism and the rise of modern organic chemistry. The enduring significance lies not only in the synthesis of urea itself, but also in demonstrating the power of scientific inquiry to challenge established dogmas and unravel the mysteries of the natural world. This meticulously written paper demonstrated the capabilities within chemical synthesis. Wöhler not only succeeded in creating urea, but provided methods that would later transform and evolve the field of chemistry as a whole. Through his work, scientific inquiry gained precedence over dogma.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.